Absolute value functions part 2. In this video, you'll learn how to describe the effects of adding a number to the expression that defines an absolute value function. You'll also learn how to explain the meaning of absolute value function in terms of distance. So let's look at absolute value. The absolute value function represents the distance from 0 on a number line. The standard form of an absolute value function is f of x equals the absolute value of x. The graph of this function is a V-shape with the vertex at 0, 0. The absolute value function can be rewritten as a piecewise function, where f of x equals x for all values greater than or equal to 0, and f of x equals negative x for all values less than 0. So let's look at some examples. The function a gives the distance of x from 0 on the number line. This table represents the function, so we'll fill in the missing blanks using the absolute value. If x is 8, then the distance from 0 would also be 8, so f of x would be 8. In the next one, we know that f of x is equal to 5.6, so we need to know what number took the absolute value and got 5.6. This will actually have two answers because 5.6 is 5.6 units from 0, and so is negative 5.6. The next value we have is x is equal to pi. The absolute value of pi will still just be pi units away from 0. Our next value of x equals 1/2 is 1/2 unit away from 0. Next we have that f of x is equal to 1. So this means that x could have been positive 1 or negative 1 since they're both 1 unit from 0. The absolute value of 0 on the next one will have an absolute value of 0 as well. And then we have negative 1/2. The absolute value would be positive 1/2. The absolute value of negative 1 will give us positive 1, and the absolute value of negative 5.6 gives us positive 5.6. The next one we are given f of x again. So we'll have two answers at positive 8 and negative 8. Now that we have the table filled out, let's graph it to see what the graph will look like. We'll start by plotting the first point at 8, 8. The next one will have two dots because we have positive 5.6 and negative 5.6, and they'll both be at a y value of 5.6. Next we have pi and pi. And then 1/2, 1/2. We'll have two numbers for this one, 1 and negative 1. 0, 0, negative 1/2 and positive 1/2. And then our two next numbers of negative 1, 1 and negative 5.6 and positive 5.6 are already graphed from previous points. So we just have 8 and negative 8 left to plot. Now we can see the line that forms. So it creates a V shape and our vertex is at 0, 0. Now let's look at transformations of absolute value. The parent function of absolute value is represented as f of x equals the absolute value of x. So the graph looks like a V with the vertex at 0, 0. We can shift the graph vertically by adding a constant k to the function. So it looks like f of x is equal to the absolute value of x plus k. So if we have a function like the absolute value of x plus 3, then our graph will still have the V shape, but now it goes up 3 units. And if we had the absolute value of x minus 1, we would still have the V shape, but it would be shifted 1 unit down. We can shift the graph horizontally by subtracting a constant h from the input. So it'll say f of x is equal to the absolute value of x minus h. So if we have a function like the absolute value of x minus 2, then our v will be shifted 2 units to the right. And if we have the absolute value of x minus negative 1, then we'll shift 1 unit to the left. We can also rewrite x minus negative 1 as x plus 1. So when we see that, we'll just know that we subtracted a negative, so we'll move 1 unit backwards. We can reflect the graph across the x-axis by making the function negative. So f of x will be negative the absolute value of x. So when we have a function like this, it just turns our V shape upside down. Finally, we can stretch or compress the graph by multiplying the function by a value which we'll call a. So it'll say f of x is equal to a times the absolute value of x. So if we have a function like 2 times the absolute value of x, it's going to compress our v, so it makes the v skinnier. If our function was 1/2 times the absolute value of x, then it would stretch our v shape. Now let's look at some practice examples using these transformations. We'll sketch a graph of each absolute value equation given. Our first equation is f of x is equal to the absolute value of x minus 2. This is in the form f of x is equal to the absolute value of x minus h. So we can see that we'll take our v shape and we'll go to the right 2 units. Our next equation is f of x is equal to the absolute value of x minus 2. This is in the form of the absolute value of x plus k. So this tells us to take the original v shape and move it down 2 units. Now we have the negative absolute value of x plus 2. So it's in the form of the negative absolute value of x plus k. So we'll take our v shape, and since we have that negative sign in front of the absolute value, it will turn our v upside down. And then adding 2, we'll shift our v up 2 units. Now let's determine the vertex of each of these equations. Our first example is in the form x minus h. So this tells us the v shape will move right 9 units. So our vertex will happen at 9, 0. Now let's look at the one below it. This is also in the form x minus h. Since it says x plus 9, that really tells us that it was x minus negative 9. So this will move our graph 9 units to the left. So our vertex will happen at negative 9, 0. Now let's look at the top right. This one is in the form the absolute value of x plus k. So this tells us we'll move up 9 units. And our vertex will happen at 0, 9. On our last one, it's still in the form the absolute value of x plus k. So we'll move down 9 units for this one, which makes our vertex at 0, negative 9. Now let's recap what we've learned. The graph of the function f of x equals the absolute value of x is a v-shape with 2 lines meeting at 0, 0. We call this point the vertex of the graph. It's the point where a graph changes direction from going down to going up, or the other way around. We can also think of this function as a piecewise function because different rules apply when x is less than 0 and then when x is greater than or equal to 0.